So, this is going to be the start of a new chapter. Technically, can't say simple harmonic oscillators because it's actually all of the above. Simple harmonic, forced harmonic, and damped harmonic. So it's a chapter on harmonic oscillation and harmonic oscillators. The first thing we have to talk about is going to be just generally stuff related to cosines and sines, actually. So imagine you have some object which is attached to a spring, and you pull it out and you let go. What you know is going to happen is it will oscillate back and forth. So since we have something that's oscillating, we have to talk about what the graphs might look like. And we'll have a particular position, and we'll look at what happens to the position over time. If we make this center position the 0 for x, and if we pull it some distance away and let go, then what you'll see happening is it will go up and down, and it will make a sine or a cosine pattern. And there are things we need to be able to extract from this. So for instance, if we look along the time axis and go from peak to peak, that is the period. And if we go from peak to peak in a different side of the whole thing, that's also the period. But as long as we're going from an identical point to an identical point, a place where the graph is doing the same thing, this point to that point is also the period. So lots of different ways of defining the period. As far as amplitude goes, amplitude is how far you deviate away from your center point. And if you look at the whole distance, that's always going to be twice your amplitude. Okay, so that's a couple of the things we need, but we're not quite done yet. If we know the period, there's another thing we can define called the frequency. And the frequency is 1 over the period. So the period is in seconds. And the frequency would be in cycles per second. So of course a cycle is going through one full cycle of your sine or cosine type function. Alright, we need a bit more than that though. Cycles per second can be turned into other things, and perhaps the most important thing it can be turned into is angular frequency. As we'll see in a later section, angular frequency, which I do want to make it look a little more like a proper omega, is equal to 2 pi times the frequency. So it would be measured in radians per second. Alright, why? Because one cycle is 2 pi radians. So we're essentially applying a conversion factor, doing a dimensional analysis. Angular frequency or angular speed, omega, ends up having a lot more use than frequency. And we will see it appear in our equations more frequently perhaps than even frequency does. Now, I need to talk a little bit about radians. In many ways, they are preferred unit for angles. Also, sort of a ratio. So radian appears and disappears pretty readily. As an example, back in your previous class, you probably learned about V is equal to R times omega. Well, V is in meters per second, R is in meters, and W is in, or omega is in radian per second. So when you multiply meter times radian per second, you get meters per second. Radian is dropped. I kind of think of it as like the Cheshire Cat unit. It just disappears, leaving behind only its grin. It comes and it goes more or less as it pleases, just like the Cheshire Cat did in the Alice in Wonderland books. So if you are taking something like V and dividing by R, the answer is an angular speed, an omega, something in radian per second. It's not just per second, it's radian per second. It's not degree per second. So you need to be careful with radians. Keep your eye out for them. They do kind of come and go. Alright. Let's see. A couple more things just to talk about quickly. We're going to find that our position will tend to look something like amplitude times cosine of omega t plus a phase. The phase represents the start point. So if we come back to this, if I pull the ball out and let it start oscillating back and forth, I can start the clock right when I let go, and that leads to the graph we have here. I could start it as it's passing through zero, headed in the positive direction. That would give a sine function. But I could start my clock, start my camera anytime I want. And based on that start, you might be at a different angle. You might end up starting out at a lower point and then coming up and hitting your high point. It doesn't have to be well aligned to a sine or a cosine. You may want to go back and review where you have learned about trigonometric functions and study up the idea of phase a little bit, because I can guarantee it's something you have seen at some point in your math classes. I will be taking it as a given that you kind of know how it works. Alright, so that's some introductory material. In the next section, we're actually going to show a little bit about how a harmonic oscillator actually comes about. And then we'll do a practice problem, and maybe I'll have a video set up that shows you how the differential equation actually gets solved. I know many of you haven't had that yet, but it's actually pretty easy to do even if you've never really studied them. It's one of the easier differential equations that exist. We're lucky. You don't have to know how to solve the differential equation to do this chapter though, so don't let that worry you for even a second, and I'll let you know when the video happens that you can skip if you don't want to see it. But next video, we're going to talk about masses on springs. Alright. Also, new background, nice space-related shirt. I know we're not doing gravitation anymore, but Cassini flying by Jupiter is what I've got on here. So I'm not always going to be dressed up in a formal shirt for these. I'm going to wear some of my more science-y related ones.